Okay, today is November 4th, 2021, and we're going to do the experiment on centripetal force, the second part centripetal force, constant mass, variable radius. Last time what we did was we did the constant radius and variable mass. Now we're going to switch it around, okay? To verify that equation for the centripetal force. What you have to do initially, you gotta get to your spreadsheet. Make sure you get to your spreadsheet. Relabel your spreadsheet. Today is the Thursday, right? That's today is lab number 7. Put your group number here. Do that right now, please. Open my group is 0. Open the spreadsheet. Should be, here you go. It's coming, it's coming. Lab number 7. We have 2 more labs to go plus this one. Enable editing. That's how the spreadsheet looks like. I'm gonna walk you through that. And I'm gonna, oh, what else you have to do? Here you go. Let me copy that and paste in the next one. Those are the notes. I did all of that there at home today, and I have to do that all over again. Everything was ready to go. Okay, today is 11:04. 21, and then the next one on Tuesday is gonna be 11:09 2021. We start at 1 today. Okay, lab report for lab 5 is due. Okay, because we had an exam report, I'm gonna give you another week to turn on report for lab 6 due next week. So I'll give you report for lab 3 is corrected there in your group folder. Don't forget to download the spreadsheet for lab 7 and relabel it. Relabel it. Uniform circular motion, second part. Data sheet, very important. I want you all to do that right now so you don't make this mistake that you do all the time when you go sign off your data sheet. At the top right of the data sheet, write the following information, one per line: the date, the group number, lab number, in this case it's going to be 7, student's name, one below the other. Okay, 1, 2, 3, 4, 5, 6 lines at most. Equipment, same equipment as before, and I'm going to walk you through one by one with the slides that I have here. Okay, so here you go. Centripetal Force Experiment 2, constant mass, variable radius. First part, the experiment has 2 parts just like the other one, but the orders are slightly different because the procedure is different too. Okay, what you have to do, you have to determine the period of rotation of the mass. In this case, the mass will not vary. What's going to vary is going to be the radius of rotation. We start with the centripetal force apparatus. You're already familiar with that. We have a rotating shaft, low frictional rotating shaft. You insert the crossbar. Don't forget to get the beveled region of the crossbar. They must face up. That's for a safety reason. You do not want this crossbar flying in your face, okay? So the crossbar should face up and should be right in here in the lined up with the rotating shaft. And gotta be the longest beveled region, that you're going to use, not the shorter one. There is a locking bolt there. They're gonna lock the bar into place. But before you do that, you're gonna start with the smallest possible radius of rotation. So just adjust the bar so this string at the shortest distance from the center of rotation. Okay, string, gonna get the bob, just like before, you're gonna measure the mass of the bob. The difference that you're not gonna change the mass of the bob, but just its radius of rotation. Hang the bob from the string. You have an indicator rod, line up the indicator rod with the tip of the bob. So tip of the bob to the tip of the rod. In the next step, you're going to measure the radius 1, R1. And this radius, you are going to log here in the spreadsheet. See, the mass of the bob is right in here. You log the mass of the bob. Don't forget to put the acceleration of gravity. Here's the first radius, R1. And what else you're going to do? If you remember what we did before, you're going to attach the spring to the rod and the spring to the bob. You are going to stretch the spring. If the spring is not in the horizontal, then you have to lower the bob, while the tip of the bob is still at the top of the tip of the rod. Okay? Adjust the height of the bob with the string. Now you must have horizontal string, vertical string, 90 degrees. If you don't do that, it's not going to be uniform circular motion. It's going to be the conical pendulum, okay? Which would be another experiment that I'm going to design for the future. Okay, so you gotta adjust the height of the experiment by adjusting the bolt so the bottom of the experiment, of the setup, touches the table. And then you clamp the experiment to the C-clamp. So far, nothing different, right? The only thing that you had to do additional was this one here. And then what you're going to do, you're going to practice to put rotating the shaft. Whoever rotates the shaft is also going to keep on looking at the bob here at a 90-degree angle with respect to this plane to make sure that the tip of the bob coincides with the tip of the rod. While you do that, be assured that you have a vertical string and horizontal spring. Shaft is rotating, bob, rod, string, spring. If you are rotating too slowly, you should have something like that. Okay, the tip of the bob is not aligned with the tip of the rod. If it's too fast, it's all the way around. Either way, you may have a misalignment of the spring and the string. So now you're ready to do the experiment, the first part of the experiment. You're going to count 20 rotations just like you did before, and you're going to do a countdown. The best way is to do the countdown. Get your timer. 5, 4, 3, 2, 1, 0. While you are rotating, only one person does everything. One person does the rotating, one person does the counting, one person does the looking here in the bob, make sure it's aligned, and that same person does the timing. Don't split this task because I don't want any difference in timing. If you split the tasks, you're going to have a delay due to the reaction time, and you're going to get a worse result. So here you go. 5, 4, 3, 2, 1, 0. 1, 2, 3. When it gets to 20, you stop your timer. Okay, that's the first part of the experiment. When you do that, what's going to happen? You're going to have not only the radius, but the time of 20 rotations it takes for 20 rotations. What you're going to do next is going to be the second part of the experiment. you're going to measure the mass, the hanging mass that is required to stretch your spring, just like you did before. But before you did that at the end, right? Right now you're going to alternate. You're going to time and get the mass. Time, get the mass, the hanging mass, and so on. That's the difference between today's experiment and the previous one. So okay, here goes second part. First part, second part. First part, second part. You're going to alternate like that. Second part of the experiment. Determine the force of the spring. The spring applies to the bob. Part can be performed without the C-clamp. The C-clamp is important because when this guy is rotating, he has some inertia. And without the C-clamp, the whole setup is going to start moving back and forth, okay? That's why we are using the C-clamp here. Okay, so here go, attach a second string to the left of the bob. The setup is not rotating. You are going to stretch it, hang the mass hanger, and add masses until the spring is horizontal, the string is vertical, and the tip of the bob to the tip of the rod. You know, we're going to measure the mass of the hanger, and that's what you document right here in your spreadsheet. Okay, watch out for the second digits. And then what you do next? You know, you're going to change the radius, the longest radius. This radius, I'm going to call it R6, okay? Because it's the longest one. The shortest one is R1. The longest one, I'll call it R6. That's better. Attach the spring, perform this experiment all over again. And because you have a different radius, you are going to have a different force that the spring is applying. Then you go ahead and do for the next radius. I'll call it R5, R3. It's going to be R5 because it's the next longest one. Okay? So that's the experiment, and then you're going to do R6, R5, R4, R3, R2, and the R1 was the first one that you did, right? Here you go. R1 for this mass, hanging mass. R6 is a good idea to keep that in the proper order, right? R5, R4, R3, R2, and you're done collecting. And then what you have to do, what else do you have to do? You gotta plot a graph of the experimental force. What's the experimental force? The experimental force is the hanging mass times G. This one right here. You're gonna plot this F experimental with this guy here. Okay? mg is going to coincide with the force of the spring. And that's what we're going to plot. If you look at the equations of the system, which was derived right in here, that's the equation, the graph should be a straight line with a slope equal to 4 pi squared. Pi is 3.14, 3 whatever, right? Yeah, 3.14 whatever. If we square pi, is going to be approximately 10. Okay, every time that you see pi square, you know, you can say that's approximately 10. So what this slope is going to be, supposed to be 40, equal to 40, close to 40, slightly less than 40. Okay, once you plot the graph, you are going to log the slope in this table right in here. See here, the theoretical value. The theoretical value is very close to 40, 39.5 for pi square. If you did a good experiment, if you have good data, you're going to get very close to this value. And what else you have to do? You're going to plot a second graph. You're going to plot, you know, it's not the x experimental, it's got to be the F theoretical. F theoretical in the y-axis. That's easier if you put the F theoretical. And the F experimental in the x-axis. Here you go. And going back here you go. See, F theoretical and F experimental right in here. Cool. F experimental is mg, hanging mass times g. F theoretical is this equation here. Okay. H9, let's see what H9 is. Is the mass of the bob. L16 square. L16 is what? Is the velocity. Okay, mv square over r. That's what the theoretical is. So plot that. What should you get? You should get a slope equal to 1. And, close to 1, right? Not equal, but close to 1. And that's what you log here. And that's what I'm going to look for. I'm going to look for the percentage difference. Log your slope of a second graph here. And if you have a good percentage difference, you're good to go. Any questions about that? Simple enough, right? Yeah.
So you said to follow the directions on the sheet. Plot F experimental on the y-axis and F theoretical on the x-axis.
Yeah, I just changed that. See that?
So you logically swap them?
Yeah, F theoretical in the y-axis.
Theoretical on the y-axis.
Yeah, I just changed it. It's easier to plot the F theoretical in the y-axis. Okay, it's easier because the F theoretical is on the right side, right? That's why. Okay, so let me stop this recording and I'm gonna upload it. Any other questions?